So now that we have introduced all the different types of functions you're likely going to see, what's the most common task you have to do in economics? Well, the most common task you need to do in economics at the introductory level would be solving simultaneous equations. Why? Because if you have demand and supply, you are supposed to find the equilibrium price and equilibrium quantity, right? So the most common type of mathematical operations you need to do would be to solve simultaneous equations. And this is also common at the introductory level because it involves no advanced mathematics. You don't need calculus. You just need to solve the set of simultaneous equation, and it's easy, right? You equate demand equals supply, 10 minus P equals to 2P minus 5. P solves up to be 5, and Q you can get from either demand or supply at price level of 5. That equals 10 minus 5. So that's just also 5. Right. So this is something you have to do, or you might have already been doing in secondary school. Solving simultaneous equations is something that all of us have learned in math class. And the name we give to this, the name that we give to this exercise is solving system of linear equations. This example we have just now, demand and supply, involves two equations. In economics, you might have more than two equations. One example would be third-degree price discrimination. Third-degree price discrimination is the case where a seller decides to sell to more than, well, the seller decides to sell to two or more markets, right? A seller decides to sell to two or more markets, and the seller charges different price at different markets for the same product, right? Third-degree price discrimination. What's the optimal pricing requirement in third-degree price discrimination? Well, third-degree price discrimination essentially is a more complicated version of the simple monopoly pricing that you might have learned. In monopoly pricing, the optimal pricing strategy involves marginal revenue equals marginal cost. In third-degree price discrimination, you have a slightly more complicated version of that. So there are actually three equations involved. The first one is marginal revenue from market 1 has to equal to marginal revenue from market 2. Why do you need that? Well, marginal revenue tells you how much money you're making from selling the last unit of a product in a certain market, right? So let's say my smartphone is selling for, well, let's say Samsung is making $2,000 on my smartphone in Hong Kong, and it's only making 1,000 in Korea. What should Samsung do? Samsung should ship more smartphones to Hong Kong because the profit margin is higher, right? And so that's not an equilibrium. That's not optimal. What would happen in equilibrium? In equilibrium, Samsung should not be shipping cell phones from Hong Kong to Korea, nor should it be shipping cell phones from Korea to Hong Kong. Because in equilibrium, it should be earning as much money from selling a cell phone in Hong Kong versus Korea. Right, that's the idea. So marginal revenue 1 equals marginal revenue 2. That's the first condition. Second condition and the third condition are the same as standard monopoly pricing. The money you make from the last unit should exactly offset the cost of producing the last unit. Because if that's not the case, you're either producing too little or you're producing too much. So that's standard monopoly pricing. So you have three equations: profit margin of the last unit produced should be the same in the two markets. You should be breaking even on the last unit in both markets. So you have 3 equations in total. That's the case when you have 2 markets, just Hong Kong and Korea. Now, a company like Samsung sells to at least dozens of countries, possibly 100 countries in the world. So, how many equations do you have? Well, if you think about it, hundreds of equations actually. You will have hundreds of equations if you really try to solve the optimal pricing scheme for Samsung in this case, because you have hundreds of markets, you have hundreds of equations. So that's not something you want to do with back substitution, right? The way we solve the demand and supply diagram in the previous case would not work when you have hundreds of equations. So part of what we want to do in this course is to figure out a systematic way to solve systems of equations, even in cases when you might have hundreds of equations. So that's the topic of linear algebra. So the definition of linear algebra would be the study of linear sets of equations. It's a very broad set of topics. For us, we would like to figure out what algorithms we have to find solutions. So algorithm sounds like a very fancy name, but it really just means ways, right? We want to find ways to figure out solutions. We want to find ways to figure out solutions. However, even after we find out the different ways we can figure out solutions with, we might not actually want to spend the time calculating the actual solutions. Even if I give you a way that works with hundreds of equations, it might take you a long time to solve the system. In particular, if you're doing it by hand, right? If you do it by computer, that's okay, but if you're doing it by hand, it will take you a long time. So sometimes we're happy if we can just figure out if there is a solution or not. And if there is, how many, if possible. Why is that the case? Why don't we need to actually figure out the solution, the actual numbers in the solution? Well, that's because if you think about in economics, very often what we're trying to do is to say there is an equilibrium, and the equilibrium is good in certain ways. We don't actually need to know the numbers of the equilibrium, right? When you draw a demand-supply diagram, and you tell people, look, demand and supply, what would happen in equilibrium is price would be here, quantity would be there, the demand balance out with supply. Price would not change, nor would quantity. That you're explaining to people the concept of market equilibrium. But did you have any numbers here? Do you have any numbers here? No, you have no numbers. So you don't need numbers to illustrate the concept of market equilibrium. You don't need numbers to illustrate how demand and supply works. For the same reason, you don't need to calculate the actual equilibrium in order to say something about the mathematical properties of economic models. Very often what we need is to say, all right, given these functions, is there an equilibrium? Is there a solution? If there is, can we say anything about the solutions? Another way you can think about it is the actual numbers might not be meaningful anyway, right? Now, as I said, in undergraduate economics, we very typically draw linear demand and linear supply, straight lines. How likely is your demand curve and supply curve actually straight? There's no reason to believe they have to be straight, right? right? In particular, if you think about a straight demand curve, what it means is that when the price gets to 0, your demand is still a fixed quantity, right? Your demand just reach a certain, let's say, right? Let's say your demand curve is a straight line, and this is 10. That means that when the price is 0, you still just want 10 units, right? That's not necessarily realistic. If you tell me iPhones are free, why don't I want 100 of them, right? If anything, I can get 100 of them and just give it to my friends. So it's not clear that the assumptions we make about the models are realistic to begin with. Demand and supply, straight lines? Maybe not. So if the assumptions are not realistic to begin with, how meaningful are the actual numbers you calculate from that, right? So once again, the reason why we draw demand and supply is to illustrate the concept of market equilibrium. We're not saying that the numbers we fit in actually make sense. If so, there's no need to figure out the numerical solutions in this case. All we need to say is, look, there is a solution there, right there in the middle, when demand intersects supply. We just need to say there is an equilibrium. So we just need to know, is there a solution? And turns out finding out whether there's a solution is much quicker than actually figuring out the numbers inside the solution, right? We can do it much faster. We can quickly say, yes, there's a solution. But if you want me to tell you the numbers inside the solution, it would take me a bit of time to figure it out. Okay. So more generally, we will also study what we can say about the properties of a set of equations. And before we move on, one thing I have to mention is that in terms of actually solving a system of equations, in undergraduate studies, if you are given a demand curve, a supply curve, and the question asks you to solve the equilibrium quantity and equilibrium price, back substitution is almost always the fastest. The methods we're going to talk about in this course, they are systematic. They work when you have 2 equations. They also work when you have 200 equations. But they are not necessarily the best way to solve 2 equations because they are not quick, right? They're not quick. Back substitution is almost what you're going to use for most of the time. One of the exceptions is that when you get to upper division courses, for example, econometrics. In econometrics, some of the questions you simply cannot solve with back substitution. You have to use linear algebra. But at least for the next 1 or 2 years, you typically should be using back substitution instead of the methods we talk about here. So we're now going to investigate what we are doing when we are solving system of equations. Let's take a look at these 2 systems. Which one is easier to solve? Which one is easier to solve? Now, if you look at these 2, I think it's fair to say the second one is easier to solve, right? The second one at x2 is already solved, right? x2 equals to -2. So all you're doing is solving x1. Whereas for the first system, you actually have to solve for x2 and x1. But the thing is, if you try solving both systems, you'll realize they have the same solutions. They have the same solutions. And the reason that's the case is because they're representing the same system just in different ways. In particular, the relationship between the 2 of them is the following. System 1's equation 2 equals to 2 times system 2's equation 1 plus system 2's equation 2. I've color-coded them to make it easy to see. So you can verify that's true, but it's quite easy to see, right? So you have 2 times x1, so you have 2x1. You have minus 2 times 2x2, so that's minus 4x2, plus x2, that becomes minus 3x2, and then 5 times 2, that's 10, minus 2, that becomes 8. So system 1's equation is a combination of system 2's equations. And one way you can think about it is, really there is no new information between the two systems, right? There is no new equations. They're just combinations of each other. So they represent the same system, but one is easier than the other to solve. So an algorithm to solve a system, would be to get from a complicated system to a simpler system, and from the simplest system to the simplest system, and the simplest system would be the solution. It's the solution, right? So we need to get from step 1 to step 2, and from step 2 to step 3. This might be stating the obvious to you, right? After all, that's kind of what you do with back substitution. You substitute one function into the other, and hopefully you would be able to get the solutions at the end. So this is what we do it when you try to solve a system of equations. And how do we pin down what we're doing precisely? Right? Can we pin down what we do precisely? Well, yes. Let's look at the first pair. What are we doing going from system 1 to system 2? Now, if you look at system 1 versus system 2, the first equation is the same, so we are not doing anything with the first equation. But where in the second equation, we go from something with x1 and x2 to something just with x2. How do we do that? How do we do that? One way to look at that is the following calculations. If you subtract 2 times system 1's equation 1, the blue equation, from system 1's equation to the red equation, you get system 2's equation 2, the green equations, right? You can look at it. It should be right? x1. So, 2x1 minus negative 2 times x1 would be 0, right? Negative 3x2 minus negative 2 times, negative 3x2 plus negative 2 times negative 2x2 would be plus 4x2, so you end up with just x2. And finally, you have 8 plus negative 2 times 5, so that's minus 10. That leaves you with negative 2. So you can in fact get system 2's equation 2 from a combination of system 1's equation. What you're doing is adding multiples of one equation from that of another. Okay, that's what you're doing. Adding multiples of one equation from that of another. Next step, how do we get from the second system where we already have x2 equals to negative 2 to the one where you actually have the solution, x1 equals to 1. Now, there's nothing we need to do with equation 2 anymore. It's solved. All we need to do is to solve equation 1. So how do we get from x1 minus 2x2 equals to 5 to x1 equals to 1? That's how you do it. All you need to do is to plus 2 times x2, right? So you have system 2's equation 1, the blue part, plus 2 times system 2's equation 2, which is the red equation, and that gives you x1 equals to 1, the green equation. So once again, what you're doing, you're adding multiples of one equation from that of another. It turns out you can always solve system of linear equation by adding multiples of one equation from that of another. You can always do that if they are linear equations. Matrix notation is there to help us with that operation. Now, for 90% of the population, matrix means guys who can dodge bullets by bending their, bending their body. Now, for the 10% who study mathematics, matrix means calculations that we need to do in this course. So, and something for you to follow is that if you have the textbook, we are following the order of the textbook. We are now at chapter 1.2 of the linear algebra textbook. We pretty much will be following the same order. The first thing I have to mention is the notations that we're going to use, and there are two of them. The first is the idea of a factor. Factor is simply an array of numbers, 1, 2, 3, right? We enclose the numbers with a square brackets to make it clear that they are an array. Obviously, you can have more than 3 numbers, so you can have b1, b1, b2, b3, b4, bn, right? So you could have many, many numbers. And factors are typically denoted by a lowercase alphabet with an arrow at the top. Okay, lowercase alphabet with an arrow at the top. This is not universal. This is not universal because some textbook would simply use a lowercase letter, and some textbook would use a lowercase letter with that is bold, right? So it depends on the textbook. But in our course, I will use this notation throughout. A lowercase alphabet with an arrow at the top to denote a factor. Matrix is a grid of numbers. For example, in this case, you can see that the first row has numbers 1 and 2. The second row has the numbers 3 and 4. The first column has numbers 1 and 3. The second column has the numbers 2 and 4. So there's a grid of numbers. You can have more than 4 numbers. You can have many, many rows and many, many columns. The notation for matrix is pretty consistent. Almost everywhere, a matrix will always be denoted as an uppercase alphabet. So this is very consistent in most textbooks. Uppercase alphabet. Some additional concepts about matrix is the idea of the size of a matrix. So how big is a matrix? How big is a matrix is described by its size. Size is the number of rows multiplied by the number of columns. So what's the size of the matrix here? 1, 2, 3, 4. The size is 2 times 2 because it has 2 rows and 2 columns. What about the factor? A factor has 3 rows and 1 column, so it's 3 times 1. Okay. Next, what about this factor b1 blah 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 bn? It has n rows, 1 column, so n times 1. Finally, for the matrix A11 blah 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 ank, it has, here's the notation, the first number represents rows, the second number represents columns. So A11 dot 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 an1 means there are n rows, and A11 dot 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 a1k means there are k columns. So the size is n times k. So that's how you describe the size of a matrix. Is factor and matrix something you have not seen? It shouldn't be. In fact, most of you probably have dealt with matrices and factors before. Namely, when you use Excel. Excel, by design, is a big matrix. You have rows and columns, so it's a matrix. You enter numbers, which you probably have done. If you try to highlight a single column, that becomes a vector. Excel can handle matrix operations because it is a matrix. Even if it does not describe what's happening that way, it is a matrix, and so the concept should not be foreign to you. You have seen matrices before. Right. How does matrix help us with equations? So there are two common ways. To represent a system of equations with matrix. The first one is an augmented matrix, which is simply putting all the coefficients to the matrix in the exact same order they appear in the system, right? So you can see you have A11x1, A12x2 equals to B1. That's the first equation. So in the first row of the matrix, you have A11, A12, B1. In the second equation, you have A21x1 plus A22x2 equals to B2. So in the second row of the augmented matrix, you have A21, A22, B2, right? Okay, so that's simply copying the coefficients. How we use that is something for we will talk about in a few slides. But that's the augmented matrix. That's the first way. The second way is with a matrix equation. Matrix equation is an equation, as you can see, is A times X equals to B, where A is a matrix of the coefficients A11, A12, A21, A22. X is a vector of the variables x1 and x2, and B is a vector of the constant term b1 and b2. Now, how exactly does this work is something that we'll talk about in the next lecture. We're not going to talk about that in this lecture. These two ways of representing a system of linear equations have different purpose. You solve them in different ways. The first method, augmented matrix, you will not see it again beyond this course. It's not particular. It's helpful when you actually need to solve for a system of when you actually need to solve the system. It's in particular when computer solves for a system of equations. It would use a method very close to what we're going to do in a moment. So it's useful in this course in actually solving system of equations. But beyond this course, as I said, beyond this course, you pretty much would use backward substitution. You use back substitution because back substitution is often easier to do in practice. In other courses, you would be using matrix equation, primarily in econometrics. Econometrics, you would certainly see matrix equations. It gives us another way of solving a system of equations. And one of the appeal of that is that we can write down the solution as a formula without actually solving the numbers. So if you think about these, if you ignore for a moment that A is a matrix and X and B are factors, if you pretend A, X, and B are numbers, what would you do if I asked you to find X? If you treat them as number, the first instinct would be divide A over to the other side, right? That would give you X. So we can represent a solution by something like this. Now, X equals to the inverse of A times B. Have we solved the system of equation? No, right? We have not solved the system of equation, but we have a formula for the solution. as I said, in many cases in economics, solving the actual numbers are not something we need to do. All we need to say, the solution exists, and this is the formula for the solution. So that's why this second representation is much more common, because it gives us a way to represent the solution without actually solving the solution. All right. We're going to explore some properties of systems of linear equations, and we have 3 of them. The first one is this one. Are the 2 following systems the same? What's the difference between these 2 systems? Well, the difference is that I swap the rows, right? In the first system, a11x1 plus a12x2 equals to b1 is the first equation, but in the second system, it's the second equation. But that's it, I swap the 2 equations. Now, are these 2 systems the same? They should be the same, right? It's because all I did was to rearrange the equations. It's the same as if I'm asking you. All right, so this is demand and this is supply. What's the equilibrium? First is, this is supply, this is demand. What's the equilibrium? Now, there shouldn't be any difference, right? Whether I mention to you the demand curve first or the supply curve first. As long as I give you the same demand and supply curves, you have the same equilibrium. So the order of equations does not change the system. It's just rearranging. Thus, it represents the exact same situation. Demand and supply, supply and demand. Wouldn't make a difference as long as they are the same curves. For the same reason, if you use the augmented matrix to represent a system of linear equations, you can swap columns. You can swap you can swap rows. You can swap rows, and they won't make a difference. You can swap the rows, and they won't make a difference. For the same reason, because each row represents an equation. You can swap the rows, and there won't be any difference. In fact, you can swap the columns too, and it also won't make a difference, because swapping columns would simply means that you are mentioning the variables in a different order. So, currently, I have something like I put x1 first, followed by x2, followed by a constant term. If you swap the columns, if you swap the first and second column, you're just simply mentioning x2 first, and then mention x1. That wouldn't change the system either, right? That wouldn't change the system either. That wouldn't change the system either. Now you cannot swap the third one though. Yeah, swapping the third one will be different. So you can swap the first 2, but you can't swap the last one. So generally we don't swap columns that often, but we swap rows pretty often. So let me write it down. So you can also swap columns, except the last one. You can't swap the last one, but you can swap any other columns, because you're just saying that, okay, we're just rearranging which variable you mentioned first. So it's okay. Next, the second property. Do the following systems have the same solution? What did I do? If you look at it, I highlighted what I did. The first system is the original one. The second system, I multiplied 2 on both sides of the equation of the first equation, and I multiplied 3 to both sides of the second equation. Are they the same system? Well, you should see that they are the same system, because if I'm multiplying a number on both sides, you can equally cancel them out, right? You can cancel out the 2, and you can also cancel out the 3. Then you get back the original system. So multiplying equations with a constant does not change the system because you can always cancel the constant term out from both sides. For the same reason, multiplying rows of an augmented matrix with a constant does not change the system. You can multiply a constant, a number. You can multiply a number to a whole row, and that would not change anything. Okay? The third property. Do the following system have the same solutions? This is the most complicated one, so once again, I color-coded what I'm doing. What I'm doing, the first system is the original system. In the second system, I added the second equation to the first. So that's why I color-coded them. Just let you see what I did. Does this change the system? Now, once again, let's think about it. Given that a21x1 plus a22x2 equals to b2, that's the second equation, right? Given the second equation, and if you look at the first equation, you can cancel out what I add, and you would get back the original system. So when you're adding the same thing on both sides, that's the same as saying you're not adding anything. Yeah. So this is probably the hardest concept to get. Adding one equation to another actually does not change the system. It does not, because you can always cancel out what you have added, and you would just get back the original system. What do I want to say? One way to interpret what's happening is that you're not adding any new information to the system when you're just adding one equation to another, right? You're still having two equations and two unknowns. You're not adding anything new. What would change the system is if you add a third equation to the system. That would be completely different. But if you're just adding the two equations together, you're not adding any new information, so the solution should not change. All right. I forgot to mention in the previous slide is in the second property where when you're multiplying constant term to equations and nothing changed, there is actually an economic interpretation of that, and that would be money neutrality. Have you learned of that concept in macroeconomics, money neutrality? Let's say your income goes up by 100% tomorrow, right? Let's say your income goes up by 100% tomorrow. But the prices of all products also go up by 100%. Has anything changed? No, right? You just have inflation and you are as wealthy as before. So that's the same idea as what we have just in the previous slide. Everything doubled. The system has not changed. The economy stays the same because you can just equally cancel out the increase in money supply and you would be back to the same situation. All right, so the final property is if you add one row of the augmented matrix to another, this does not change the system. This is very hard to understand unless you think about what it represents. The augmented matrix represents system of equations. Each row represents one equation. When you add one equation to another, it doesn't change the system. So when you add one row to another in the augmented matrix, it doesn't change the system. What about subtraction? I've just mentioned addition and multiplication of constant term. What about subtraction? What is subtraction? Subtraction is essentially adding -1 times another row, right? If you're subtracting a row, you are adding the -1 times another row. Since addition of a row does not change the system, and multiplying a constant to a row does not change the system, so adding a constant times a row should not change the system. So subtraction also does not change the system. So these are all the properties we need to know. Together, they are called elementary row operations. Swapping two rows, multiplying by a row by a non-zero constant, and adding a multiple of a row to another. These three operations are called elementary row operations, and none of them would change a system. They don't change the system. Why do we need them? What's the use? The use of them is that it can help us to solve a system of equations. The algorithm we talked about in the previous slides, where we subtract or add multiples of one equation from that of another, it now translates to adding or subtracting multiples of one row from that of another in the augmented matrix. So by swapping rows, adding rows, and multiplying rows with a certain number, we can solve system of equations. And I think we have to do that next time. We're going to do that next time. Right? So just see if we have enough time. Well, we do have some time. So I'm going to demonstrate it once today, and we'll go over it again next time. Right, so let's say you have this system of equation, right? It's three equations, three unknowns. You have three equations, three unknowns. How do you solve this equation? All right, how do you solve this equation? We're going to say that you can do that. You can do that by using elementary row operations, right? So you can also think about it with the system. You can like adding equations, subtracting equations. Maybe we can do that first, and then we will switch to the elementary row operations notation, right? Because it's ultimately identical. Right? Okay, so what can we do? Now, this is the system of equation we're trying to solve. I'm going to propose a series of operations that in the end, should give us the solution. All right. So we start with the first step. We're going to add the. Let's see. We're going to add the first row to the second row. We're going to add the first row to the second row, right? Okay, we're going to add the first row to the second row. Why do we want to do that? Now, the reason why I want to add the first row to the second row, so let me write that down. Add first equation to second, right? We're going to add the first equation to the second. Why do we want to do that? The reason why we don't do that is, if you notice, the first equation has an x and the second equation has a negative x, so they cancel out. So if you do that, right, unfortunately, this exercise would involve a lot of copying, but it can't be helped. So I'm just going to write down what we have right now. And then what we're now going to do, what we're going to do is add the first equation to the second. And the reason why we do this is we want to make use of the fact that the x cancel out, right? The x cancel out. Although you might ask, is it necessarily faster immediately? It might not be obvious immediately, but later on it might be more. In later steps, you might notice that actually helpful. All right. Okay, so we cancel out the x, we add, and the 3y minus 2y becomes one single y, and you have y plus 3z equals to 5, 2x minus 5 plus 5, 2x minus 5y. So this is the same, we haven't changed it. 5z equals 17. In some sense, this is something you want because if you are doing back substitution, you have y equals to 5 minus 3c, which is something you can substitute in another part. Right? Now, what we're going to do next is that we're going to add -2 times the first equation to the third one, right? So in the first time, we're going to do it slower, and I want to make sure that I'm keeping in time. Right, so once again, it involves a lot of copying. As I said, this method is not going to be faster in practice. It's just systematic. So you're not going to see it beyond the math course. Right, so -2 x minus 2x minus 2x, you have x minus 2y plus 3c equals 17 minus 2, 9. Once again, the point is that we want to cancel out. The point is that we want to cancel out the 2x. That's the main reason why we do this. And after this step, what you have is x minus 2y plus 3c equals to 9, y plus 3c equals to 5, and negative y minus c equals to -1. All right, so we're going to do one more step. Actually, well, two more. Add the second equation to the third equation. Once again, we do that because we want to cancel out the y this time. We cancel out all the x in the second and the third equation. Now we're going to cancel out the y in the third equation. Right, so this is -y minus x plus y plus 3c equals to -1 plus 5. Right, and what we have now is x minus 2y plus 3c equals 9, y plus 3c equals 5, and then 2c equals 4. Right, so it's quite clear that if you divide the third row by 2, you get what c is, which is 2. For space reason, so we're going to do, we're going to do two things. Divide third row by 2, right? That gives you c, right? There's one more thing I want to do in this case, is that I also want to subtract. We want to subtract the second row by 3 of the third row, 3 times the third row. Okay. Right, so that's the two things I want to do. Divide the third row by 2, which gives you C equals to 2. And then I want to subtract 3 times the third row from the second, and that gives you C equals to 2, right? And then you subtract that from, then the other one, you get y equals to -1, I think. And then you just have x left, which I haven't solved yet, but you get the idea. Right? And if you solve it, you can actually substitute that in, and then x would equal to 1, right? So you can see the process. You keep multiplying rows, subtracting or adding them together. You end up with the solution. It is not fast. It is systematic. The benefit of this is something you can do with many equations. This is something you can teach a computer to do. For practical purposes, this is not what you're going to do, right? So it's just something you have to know, because it's an essential process in solving very complicated systems, right? Yeah. So this is an example. We're going to do more of that next time, and I'm going to see you. Well, if I come back on time, I probably will be here for the tutorial. So if you're here for the tutorial, I'll see you next week. Otherwise, I'm going to see you in 2 weeks. Okay? Okay. So Python is a programming language. So how to use Python? There are 2 ways to use Python. You can run Python from the command prompt or terminal, right? Command prompt for Windows and terminal for MacBooks and Linux. So you just open terminal and type Python. You can do that. But that's not usually how we do it in classes like this, because first, there's no way for me to provide you with instructions easily in that case. And second, whatever you do, it goes away when you close the terminal. So we're not going to use that. Instead, we're going to use the second method, which is running Python from a browser. So how do you get Python? I've mentioned that in my email, and also I've now mentioned it I've explained it on Blackboard. If you want to have offline access to Python, so that means that you can run Python without internet, you can download Python installation from this address, continuum.io/downloads, and download the Python 3.6 version for your operating system. Right? Anyone have done that already? Anyone? Some of you, not a lot, right? Now, for this method, once you install Python, you search for Jupyter Notebook, and once you click on that, it should launch an interface that gives you a selection of files. And the files that you want to download the files from Blackboard to either your My Documents folder if you're using Windows, or to your home folder if you're using Mac or Linux. So that's what you need to do. As I mentioned in my email, you need a relatively new computer if you want to install Python on your own computer, because the step where it takes a bit of time for the interface to open after you click on the link. As someone has just shown me, right? It takes quite a bit of time. So if your computer is not new enough, then it might find a wait too long. If you're using a MacBook, a recent MacBook, it should be MacBook Air or MacBook Pro. It should be fine. I'm not too sure about the 12-inch MacBook. It might not be fast enough. I've not tried that. Similarly, if you're using Windows, if you're using a recent Windows, like say less than 5 years, and if it's more than $5,000, it should be fine, right? So that's offline access. What if you don't want the offline access, or if the offline access is too slow? Well, you can use the online access provided by this course. And you can access the online access with econ1101.econ.chuhk.edu.hk:8000. This one, for this to work, you need to be connected to CUHK Virtual Private Network, because the server is in my office And CUHK does not allow outside connection to computers on campus unless you are connected to the virtual private network. And that includes university Wi-Fi. So CUHK, even with CUHK Wi-Fi, you still need to use VPN. So